Hello everyone, the name of my presentation is Analysis of Subsidence Characteristics in Northern China's Mining Engineering Areas with SBAS-InSAR, a digital monitoring approach based on satellite remote sensing. And the presentation is divided into 5 parts. The first part is summary of my research. And this study employed SBAS-InSAR technology to accurately monitoring in surface subsidence in coal mining area in northern China. Using Sentinel-1A data, we acquired millimeter level velocity and displacement time series, followed by atmospheric correction and phase processing. Analyzing the subsidence morphology, we observed a pattern of continuously subsidence on the western side, relatively stability or slight uplift in the central region, and widespread west-east dipole pattern on the eastern side, with limiting rate reaching -25 mm per year and positive 20 to 25 mm per year, respectively. The cumulative uplift in the eastern region is projected to reach approximately 30 mm by 2024. Regarding the characteristic of subsidence zone, we found its morphology resembles a string of beds and funnel with clear boundaries, closely matching mine operations and secondary faults, exhibiting significant structural coupling and residual compressive phenomena. This helps us accurately identify risk areas. SBAS-InSAR technology provides an efficient monitoring method for coal mining subsidence, offering scientific support for risk prevention and control. And the second part is introduction. As one of the world's largest energy consumers, China relies heavily on coal as its core energy source, and its strategic importance has become increasingly prominent amidst the sustained high-speed growth of its national economy. Subsidence not only alters the nature landscape and reduce land use value, but also poses a threat to agriculture. Simultaneously, horizontal ground deformation and differential subsidence with mining areas damage infrastructure. But now, the existing monitoring technology has several limitations. The first is that in coal mining relies on methods like spirit leveling, static GPS, and kinematics GPS. While they can yield data, they are labor-intensive, time-consuming, costly, and difficult to maintain over a long period. And the traditional monitoring methods, which depend on sparse point measurement, often fall short of operational requirements for accurate and temporal resolution, introducing biases into subsidence deformation analysis and under the need for improvement. So there is very urgent need for the change of monitoring technologies. And the InSAR technology has several advantages and applicability. The first that InSAR is an advanced technology for surface deformation monitoring with all-weather day and night capability. It measures deformation over wide areas with high accuracy and yield millimeter scaling estimates. And the technique captures subtle displacement and includes several variants. D-InSAR, PS-InSAR, and SBAS-InSAR, which are suitable for deformation monitoring across different temporal and spatial scales. And SBAS-InSAR can provide high precision, full coverage, and dynamic subsidence monitoring results. And the SBAS-InSAR technology compensates for the shortcomings of traditional methods, show unique advantage. So the SBAS-InSAR and besides that, the SBAS-InSAR is very suitable, is well suited to the Taiyuan Shanxi coal mining areas. We can use this technology to monitor the subsidence in these districts in long term, cumulative and spatially heterogeneous. And the second part is the research background. And the Xishan coal basin as a major coal production base in Shanxi province, the Taiyuan Xishan coal mining areas plays a very key role in province coal sector. Since late 1950s, output from Xishan mines has increased and at the time accounted for more than 30% of provincial production. After decades of large-scale extraction, resources have become progressively dilapidated, and surface subsidence has intensified with broad spatial reach. The latest survey indicates that subsidence has grown a lot, and in Xishan coal mining areas there is multiple disasters caused by the ground subsidence. So we use the SBAS-InSAR to monitor the subsidence in Xishan coal mining areas. And the research methodology is the first part. The first one, we use the data acquisition and processing method to get the Sentinel-1 satellite data in ESA, and we use the SARscape software to monitor, to do the data processing. And at the same time, 90-meter resolution DEM data are provided by National Geographic Information Public Service platform. So the second part is the basic principle of SBAS-InSAR. The SBAS-InSAR technology significantly improved the data sampling rate by combining the multiple SAR images with small reference distance, thereby achieving high precision monitoring of the surface deformation. And the data acquisition and processing flowchart is shown before. The first one, we should get the deformation and deformation time seriously data, and then we use SARscape software to follow this flowchart to get the atmospheric phase data, and then we use the DEM to get the correction coefficient, and finally we get the deformation time seriously data. This is the data processing process. The first, we get the differential interferogram, and the second, we get the coherence coefficient map, and at last we get the differential map. And the last part is result analysis. From the subsidence velocity deformation map, we can get the relationship between surface deformation and mining areas in Taiyuan. First, based on the SBAS-InSAR, an annual average deformation rate map on the ground surface in Taiyuan from 2024 to 2025 is obtained, showing the spatial relationship between surface deformation and the Xishan coal mine gulf. And the figure shows that the distribution map of the vertical annual average deformation rate inverted from the ascending and descending data, respectively. The yellow indicates the surface uplift, and the blue indicates the surface subsidence. And we can see that the subsidence exceeding the minus 20 millimeters per year, and uplift reaching the positive 20 to 25 millimeters a year or more. And we can see some we can see some more results from the figures. The west subsidence and east uplift pattern. The map reveals a clear west subsidence, east uplift pattern, with continuously blue subsidence belts along the Xishan mountain front, and the eastern city shows extensively yellow-orange uplift. Area B and C are characterized by the gulf-controlled subsidence along the mountain front, with a string of beds, morphology peaking at funnel centers and tapering outwards. And we can see that the subsidence time series for area B and area C shows annual total of -18 to -22 millimeters and -20 to -24 millimeters respectively, with slightly lead. The area D shows extensively orange uplift, co-located with recharge zones, backfill areas, and major infrastructures in the eastern city. The uplift likely reflects strata rebound from rising groundwater and release of consolidation after foundation peat backup. And we can see that the annual differential between D and A is 63 millimeters. Between D and B or C is 50 millimeters respectively. This construct implies the strong differential strain or linear work across the deformation boundaries. So we need to pay more attention to these areas when we build some infrastructures. And this is all my research. Thank you for the listening, and thank you to give my advice about my research.